Welcome to our graphical methods shear and moments diagram example for a uniform load, and we got the uniform load from a person, 116 pounds, sitting on our skateboard, and we said that they were evenly distributing their load between the wheels. And so we determined that 116 pounds distributed over 29 inches would give us, which was the distance between the wheels, would give us 4 pounds per inch, and we found the reaction, since it's symmetric, of 58 pounds per wheel. And so we want to go ahead and draw using the graphical methods instead of the equations like we did in class. We want to draw the shear and moment diagram for this. And to help us using the graphical method, I do have the relationships for shear and moment shown on the right side of the page, so we know that the area under the shear diagram is the moment and the area under the load is the shear. So as we draw our shear diagram, we want to make sure that we label our drawing. And so we can start adding things in. We said that there is no load at all between 0 and 5.5 inches, so there's going to be no shear. And let's mark just where the ends of our boards and our wheels are to make this a little bit easier. So there's our 0 shear. Now we have 58 pounds occurring at the first wheel, but I also have 4 pounds per inch coming down. So should I jump up by 58 pounds? Do we jump by 58, or do we only jump by 54? That's a common question students ask, and so the way to think about this is that 4 pounds is occurring per inch. If you're right where it starts, you've actually are at 0 inches. So if you multiply your 4 pounds per inch times 0 inches, you really only have 0 load there. So exactly where that load starts, it doesn't affect the shear diagram, and so we would jump up simply by the 58 pounds, and so we're going to have 58. But the moment we just move the tiniest bit to the right of the wheel, then we start dropping by 4 pounds per inch. And we could sit and start making marks, okay, -4, -4, -4 pounds, but we see that the 4 pounds is constant. The 4 pounds per inch is constant over 29 inches. So we can actually come clear over to the second wheel and just subtract the area under the load diagram up to that point. And so the area under our load diagram would be nothing more, area of our load is simply equal to the 4 pounds per inch times 29 inches, which not surprisingly would give us back our 116 pounds. So we're going to drop by 116 pounds. And so we're going to find that we'll end up somewhere about right here at -58. And we need to connect the 2 points, the two 58s. So we need to decide, are we going to connect them with a straight line, or do we have a curved line? And so to know that, we have to go back to the load, because we said that the slope, dv dx, the slope of the shear is just equal to the load, or negative of the load. So if that load is constant, like our constant 4 pounds per inch, that means our slope is constant. So let's see if I can connect that. It's pretty good. All right, and then we get to the next wheel, and at the second wheel we again have 58 pounds straight up, so we can just go straight up, which brings us back to 0, and then we have no load at all in the last 5.5 inches, so we have 0 shear. And so as we look at our shear diagram, we can identify 2 separate areas, area 1 and area 2. Now it does turn out that area 1 just equals to negative area 2. They're going to be the same size, but we would need to determine what the x value is of the leg of the triangle if we were really going to say determine what those areas are. And so to determine what that x value will be, the simplest way to do it, well, we could observe by symmetry that it has to be half of 29. But let's show how we really calculate that, because not every problem will be symmetric. And so to get that x, all you have to do is take the height of the triangle, which would be 58 pounds, and divide it by the rate at which we were dropping. And we were dropping by the load. So we were dropping at 4 pounds per inch, and that actually turns out to give us 14.5 inches. Okay, and so our x is equal to 14.5, which matches the symmetry of the problem. And of course, we can identify our Vmax, and I'll say the absolute value because we have the same amount, positive and negative, and that's just going to be our 58 pounds. It's always good to identify our maximum shear and our maximum moment from our diagrams. So we are ready now to find our maximum moment. So we can get ready with our moment diagram and label it, so anyone else looking at this knows what we have going on. So we have our pound inches. You can call them inch pounds. It's the same thing. And so we again bring down, just to keep things clean, changes in the shear diagram or loading that would affect. And so since the shear tells us about our moment, and the shear is equal to the slope of our moment diagram, where the shear is 0 is important because that means the slope is 0, and that's always like a max or a min on a curve. So we want to know where that's at. Alright, so moment is just the area under the shear diagram. In the first 5.5 inches we have 0 shear, so we have 0 moment. Then we have this area 1, so we're going to jump up. It's a constant area in that, well, it's a constant area. So we need to find out what that area is going to be equal to. And so we can solve our A1 as the area of the triangle. So we just have our 1/2 times our height of 58 times the x, which we found out to be 14.5. And that's going to turn out to be 420.5. And so if we move down to our moment diagram, we are going to jump up to a point somewhere about right there that we can say is 420.5. But the question is, do we come up with a decreasing slope, an increasing slope, or is it linear? So let's go back and look at the shear, because we know our slope is equal to the shear. For the slope to be constant, our load would have to be constant, and our load's not constant. So we can get rid of the linear. Our load is changing, so our slope should be changing, or our shear. Our shear isn't constant, our shear is changing, so the slope of our moment diagram should be changing. And as we look at the magnitude, so look at the magnitude of the shear diagram, the magnitude gets less with every inch we go over. So every inch we're adding less and less magnitude of shear. So we're going to have less and less slope. So decreasing the magnitude of shear is decreasing the slope. So we'd be looking at having a decreasing slope. And I'll just kind of connect these pieces to finish it up. So there's what our moment diagram would look like from the first half. We now know we have negative area and negative shear in our shear diagram, and we still have a magnitude of 420. It's just negative, so that's going to bring us down to 0. And to get there, we will have a changing slope, but is it increasing or decreasing? So let's look at the shear, and we can see that the magnitude of the shear gets bigger. It's increasing with every inch, so our slope should be increasing. And so there we have an increasing slope. And then finally, in the last 5.5 inches, we're just going to be 0 because there is no shear. And to remind you, if you struggle with increasing versus decreasing, remember, we can draw a person walking up the hill, and we can see that it's getting easier for them because the slope is decreasing as they get closer to the top of the moment diagram. But if that person were to continue over and start heading down, they've got an awfully steep slope to deal with because the slope is an increasing slope. Now you can also look at the equations, you can think of concave and convex, whatever works for you to determine how the slope would work. And finally, as we look at our diagram, we can see that our maximum moment will be equal to 420.5 pound-inches, or inch-pounds. And it's interesting to note that on the first shear example with the skateboard where 170 person stood on it, but we had point loads close to the wheels, our max moment was actually less than for a uniformly distributed load that was only a 116 pound person. So think about how the loads are distributing and how different, though the shear is almost half on this problem of what the max shear was for a 170 pound person standing close to the wheels. So shear and moment diagrams can tell us a lot of useful information.